Hi, I am recording this video to help you with your problem situation, right? So the problem situation is about the Wheastone Bridge. So I will make a simulation, some analysis, and I will show you my prototype for the solution for the problem situation, right? So here, uh, here, I have Proteus. Yeah, Proteus is a simulation software. I will use this to make some simulation. Uh, so First, I will add the voltage source, a DC voltage source, a voltage source right there. Uh, this is the one that is going to generate the voltage that we will use to measure. Uh, I will define this as a 5-volt voltage supply. I can generate 5 volts with some batteries, with a lab power supply, with everything, right? We just need 5 volts DC. Then I can add some resistors. I will add here a resistor, right? A resistor. I can I can rotate this with the plus sign. So I will add two resistors first. So I have R1 and R2. By default, they are 10K resistors, 10 kilo ohms. And I will generate here some loop. Okay, I will add also the ground pin, and that's my circuit. So we already know that this configuration, it's a voltage divider, right? We have two resistors in series, and these two elements are connected in parallel with a power supply. That's a voltage divider, right? I have here one voltage, and I am going to generate another one here that is a fraction of this one. In order to measure, I will add a voltage proof in here between the two resistors. So right now we already know the resistors have the same value, so I am expecting here half of this voltage, right? If I run the simulation, I get 2.5 volts. That's perfect, right? I have 5 over 2, that's 2.5. Okay, so that's the concept of voltage divider. I can add two other resistors. I will add them up here to the right, R3 and R4, and I can connect them in series. And if I connect this to ground and this to voltage, I will have a second voltage divider, right? Right now, it will be the same value because these are the same. So this branch have the same voltage as this branch, and they have the same voltage as the power supply, right? Because they are in parallel, and parallel elements will have the same voltage. So if I put here a voltage proof, I am expecting to read also 2.5 volts, right? I have 5 here, so half of that will be also 2.5. And we can see that I have 2.5 volts here and 2.5 volts there. In this configuration, now I have the Wheastone bridge, right? If you remember, the Wheastone bridge was 4 resistances. They are connected in series, these two connected in series, and they are in parallel, right? And I can measure the voltage difference here, right? Let me add here a DC voltmeter. So let me stop the simulation, it's running. So if I add a voltmeter and I reference this proof in this node and this in that node, and I will left these two to see the voltage. Maybe let me just mirror this, so maybe it will be to the other side. Perfect. So now this voltmeter will give me the difference voltage between this node minus this node, right? Here I have the positive minus the negative. Will give me the difference. Right now I have the same voltages in those branches, so I am expecting to get 0 volts there. And I get 0 volts, right? 2.5 minus 2.5, it's 0 volts. Now, uh, let me open one node here. Now, we already know that we have one resistor in series with another, and this branch is in parallel with two other series resistors, right? And this node is connected to the voltage supply, and this is connected to ground. And that's our configuration. And here we are reading the voltage there. Okay, if I call this R1, R2, R3 and R4, it's the same as ours in our simulation, right? Just I have this vertical, but R2 is connected to R3, R1, sorry, R1 is connected to R3, R1 is connected to R3, R1 is connected to R2, R1 is connected to R2, R2 is connected to R4, R2 is connected to R4, R4 and R3 are connected, here are connected. So it's the same circuit, it's just redrawn in a different way. So then I can calculate the voltage here, right? I have voltage in the simulation, this is 5 volts. I can calculate the voltage in this node and the voltage in this node, right? We already know that we can use the formula for a voltage divider, right? So VA, it's equal to the input voltage times the resistor in the lower side, R2, over the sum of the both resistors, right? R1 plus R2. So that's the formula for VA. For VB, the voltage in this node, in node B, it will be the same. It will be input voltage times the lower resistor, R4, over the sum of both resistors, R3 plus R4. So we already know that. So the voltage read here, B, will be equal to VA minus VB. Okay, perfect. So we know that that's equal to the input voltage times R2 plus over R1 plus R2 minus the voltage in B. It's input voltage times R4 over R3 plus R4. So I have this common factor being, so now the voltage can be the input voltage times R2 over R1 plus R2 minus R4 over R3 plus R4. So now the idea of the Wheastone bridge is that if I already know 3 of these resistors, I can calculate the fourth one. How? Making this voltage equals to 0. So right now, I can compare this relation, right? If this voltage equals to 0, this equation will be equal to 0, R1 plus R2 minus R4 over R3 plus R4. Okay, now I can pass dividing this value, right? And this is a 0. 0 over anything will be 0. So I get that 0 equals to this thing. Let me just copy it so I don't need to write it. Okay, 0 will be equal to this thing. Okay, that's because I pass being dividing. Perfect. The input voltage dividing. Now I can pass this to the other side. So R4 over R3 plus R4 equals to R2 over R1 plus R2. Okay, that's fine. Now, this tells me that if I know 3 of these values, I can already calculate the other one, right? Because we have here 4 values. If I know 3, I have just one unknown. So I can calculate that, right? And that will be really easy. So that tells me that the relation between R3 and R4 should be equal to the relation here, right? So for example, if I make this a potentiometer, I will change this for a potentiometer. Let me add here a potentiometer. This one should be okay. So a potentiometer is a variable resistor, so I can change its value between one of its terminals and the common one that is called the wiper, right? So I will connect this here. So this will be just a resistor, right? I will suppose that I have a potentiometer of 10K. Let value. I don't know why it's not letting me. And edit properties. Okay, perfect. So I will suppose I have a 10K potentiometer that the maximum value when I am measuring. Let me run the simulation just to check this. When I change this to the lower side, I will get 10K. When I go to the upper side, I will have 0 ohms, right? Because the resistance from here to there, it's 0. Here it's a little more, here a little more, until I get to its maximum value, right? Right here, I will get the maximum value of this resistor that in this occasion, I will put 10K, right? So if we see here, when I have 0 ohms there, I have 4.5 volts. It's not 0, right? It's a little bit. I will get 5 volts when it's 0. Then as I am increasing, this voltage it's decreasing. Okay. And this one remains the same, right? 2.5 volts. So when I get here the 10K, now these two voltages are the same. So this is 0, right? So in this case, I am generating here a relation in which these two resistors are the same. And when these are the same, I get 0 volts. If they are different, I don't get 0 volts. So I can change this resistance value and stop when this voltage is 0, and I will know now that the relation between these two is the same as the relation between these two. So that's a really interesting result, right? Let me change the value of the potentiometer once again. So let me put now that it's a 20K resistor, a 20K potentiometer. So if I check right now, the voltage is not 0. I will move its value until I get a 0. Right now, I have a 0 because I am half of the 20Ks, right? So I have here 10Ks, and that's the same as this. So I have the same relation. So now, depending on the value here, I can get which value I have there. So that's a really useful result, right? Because I am going to give you one of these in which you are not going to know the value. So it will be like a blank resistor. And measuring one voltage, you can measure this voltage. You are going to be able to know what's the value of this resistor, right? So uh, let me put the camera. So this is my prototype, right? So here I have two batteries. That's my DC voltage source. I have a little switch to let pass or not the voltage to my circuit. Here I have two 10K resistors. This is one 10K resistor. This is another 10K resistor connected in series. That's our first voltage divider, right? Then I have these two cables that are connected to this little thing. I built this fancy potentiometer, right? So this in reality is just one potentiometer in which I am using just two LEDs, right? The middle one and one of the outer pins. And I soldered those two cables so I can connect this thing, right? And I print this little face with values, right? So I know that in this position I have 10K, here I have 8K, 7K, 6K, 5K, 4K, whatever resistance I got, right? And the idea is that I can connect in this part the fourth resistor connected to ground, and then I can measure the voltages, right? Here I have two voltmeters, right? The idea in the lab, you will have a multimeter and you can read the voltage between these two nodes, the yellow cables. Right now, I am reading the voltage between the first two resistors and the voltage between the second two resistors, right? R3 and R4. If these are the same, I suppose that I have the same relationship in resistors, right? So here I have the same resistors. Then I am expecting that whatever value I got here will be the same as here when these two voltages are the same, right? So I will start with, for example, this resistor, okay? So I don't know if it will be visible, but it's a brown, black, orange resistor. So that's a 10K resistor, right? I will connect this between ground and R3. This will represent R4. Let me just put here, right? So those. Okay. So here, uh, this is the resistor I am adding. This is this one, and this is the potentiometer, right? It's this white thing. So let me return to the camera. So if I turn on this, I will get two voltage lectures, right? Right here I have 2.9 volts. So this is for the voltage divider of the 10K resistors. So I am getting half of this. So right here I have about 5.8 volts, right? Then I have the middle here. And in this, I have the voltage divider that I am making with the unknown resistor. Right now, we know that it's the 10K resistors and the potentiometer. So if I start moving the potentiometer, this value, it's increasing to the side. So I want to get the same as 2.9. So I have to decrease its value until I obtain kind of the same value of the other one, right? So there, they are almost the same. And here it's telling me 9.8 Ks. So it means that this resistor, it's about the same value. It's about 9.8 Ks. And we know already that that was a 10K. So I already know that voltage, right? That resistor value. So this is a 10K, right? Then, for example, this is a brown, black, red resistor. So that's a 1K resistor. If I connect this between R4 and ground, right there, uh, and I turn on, I want to get this voltage to 2.9. We already know that I have to turn, in this case, counterclockwise. So, so right there, ah, it's in 1K. So that's the correct value, right? So this is 1K. And now, for example, without watching the value, I will try with a third resistor. I will put here. I turn on. Okay, I have to decrease this in order to get the other one. So this one is close to 7.3 Ks. So that's maybe a 7.2 K, 7.3 K resistor, right? So with this little circuit, with the Wheastone bridge, we are able to measure resistances and to obtain exact values of the resistances, right? The reason in which we need the second voltage divider and not just work with the potentiometer and this one is because maybe this voltage source is variable. So when you have the same voltage here, the relation of the resistors is the same independently on the voltage supply, right? It's like in our calculations, we already learned that the when this is zero, it's independent of the input voltage, right? So I can put as a power supply a 1 volt battery, a 3 volt batteries, and it must work, right? So this is my explanation. Hope it's useful for you. And in your case, you will not have two voltage meters, but if you measure between these two, you are you are searching for to get 0 volts here, right? When you get 0 volts, the relation between the first two resistors and the resistor 3 and the unknown is the same relation, right? So you can design for whatever values in the principal branch and in the second branch, right? So try not to use the same values as me, right? Use different values, so it will be more interesting for you to try that. So hope you this will be useful, and see you on class.